Greetings, doctor. My name is Dineshwaran. My matrix number is DE20033. I am representing Group 4 to present about assignment 1. So my team members are Danesh and Madan Raj Naidu. For introduction, a neural network inspired by the human brain comprises interconnected neurons adjusting connection strengths through training on data. Effective for tasks like pattern recognition, it includes feed-forward networks specialized for general tasks, convolution neural networks for image processing, and recurrent neural networks for sequential data. These networks find application in computer vision and natural language processing. For problem statement, the challenge in stop sign detection is creating a computer vision model capable of reliably identifying signs in varying conditions, including lighting, weather, and traffic scenarios. The critical role of stop signs in regulating traffic requires a solution ensuring prompt and accurate detection. The project aims to address these challenges using advanced techniques like YOLO V8 to develop a real-time stop sign detection system adaptable to diverse scenarios.
Greetings, doctor. My name is Madan Raj of metric number DE2000017, and I will be presenting about task 1. So for task 1, we were given two different tasks, which is for creation of model 1 and model 2. For model 1, we need to design our own CNN model and choose an appropriate number of convolution layer, filter, pooling, stride, padding, and dense layer, and then train the model using dataset which was given in the Google Drive. And then we need to set an appropriate batch number, and the epoch size is set at 100. For model 2, we need to select any state of the art pre-trained CNN model and combine with model 1. The epoch size is also at 100%, and we need to choose an appropriate batch number also, and we need to compare the outcome of both models. Okay, so this will be for the task 1, model 1. So this code over here is to import the data from the Google Drive. So as we can see, the CAN train length is at 156, PET trainable length is at 310, CAN validation length is at 77, and PET validation length is at 133, and PET and CAN test length is at 2. This code over here is to import the library for TensorFlow and Keras. Okay, these are the layers that we used. It consists of 5 convolution layers, one for flatten, another one for dense. So the pixels is set at 150 times 150, and the RGB channel is at 3. This will be outcome for the code above. So the total parameters is at 917921. The trainable parameters also similar, and the non-trainable parameters is at 0. So this code over here means that the pixels in each image will be divided by 255. The batch size for both trainable and validation is set at 32. So this will be the outcome. So after that, we set the epoch at 100 and train the data. Okay. Upon completion of training, we need to plot the training and validation accuracy and training and validation loss. So the outcome is that the training accuracy is at 100%, validation accuracy is at 97.62%, training loss is at 0%, and the validation loss is at 7.99%. This is for model 1. Let's look into model 2. So model 2 is actually the combination of model 1 with pre-trained CNN model. So the pre-trained CNN model that we used is DenseNet 121. So this is similar. We need to import the data from Google Drive, similar to the Model 1. This is also the library for TensorFlow, Keras, and DenseNet. So this is to freeze the layers of the pre-trained model to retain their weights during training. Okay, this is the layers. Total parameters for it is at 154, 27137, and the trainable parameters is at 838, 9633, and the non-trainable parameters is at 703, 7504. Okay, and also the pixels in each image will be divided by 255, and the batch size is also set at 32. This will be the output, and the epoch is set at 100. Upon training, this will be the final outcome. So the training accuracy is at 100%, validation accuracy is also at 100%, trainable loss is at 0%, and validation loss is also at 0%. So let's look into the comparison between both models. For the first model, which is the basic CNN model, the training accuracy is at 100%, same as using the DenseNet 121, which is at 100%, and the trainable loss for both is at 0%. So for the validation accuracy, for the basic CNN model is at 97.62, and the validation loss is at 7.99%. For the DenseNet 121, the validation accuracy is also at 100%, and the validation loss is at 0%. This shows that the combination of basic CNN model plus the pre-trained CNN model offers a better trainable process.
Greetings, Doctor. My name is Danish Sadasivam, matrix number DE200010. So I will be presenting the methodology for our task 2. In task 2, we will be using YOLO V8 model for object detection task. The object we are going to detect is stop sign in UTHM. So first step will be data collection. For data collection, we have collected around 300 pictures, including the pictures in campus and also pictures from internet, followed by annotate collected data in RoboFlow. In RoboFlow, we have annotated the data and also we have used data augmentation to boost the number of images, followed by exporting data to YOLO V8 model in the Google Colab. Once the data is exported, we can train the model in Google Colab. After training, we can test the sample image and videos of stop sign in UTHM. For this, we have collected few images and also videos of stop sign in UTHM. Lastly, we will gain the output from the Google Colab in a zip folder. In this folder, we can gain all this output of video, images and other parameters. Now I will do the demonstration for YOLO V8 model. So let's get started. So firstly, we have to import the necessary libraries for the YOLO V8 model. First will be NVIDIA SMI. Then pip install Ultralytics. Then from Ultralytics import YOLO. And then pip install the RoboFlow. This is to import the dataset from RoboFlow, the annotated dataset. Once this is completed, we can train the YOLO V8 model. In this, we will be setting the epoch to 50 and image size will be set to 100 by 100. So once it's done, now we can train the test video, which is we have taken a video from UTHM. So we will copy path and paste it to the test command. So this detection process will take some time. So now the detection process is completed for video. So as you can see here, there's a lot of predictions here. So this is the latest. So this is the detected video. So we can download this to see the output. In the meantime, we can also test using image, where we have the 3 test images. We can just directly copy paste the path and start the detection. Predict 16, test 1. So as you can see here, the stop sign has been detected accurately. We can do the same to the other 2 images as well. Two. So these are the prediction for the images. And the last step will be processing the other parameters and output into a zip file. So this is the zip file. So in the zip file, the contents will be the F curve, P curve, and so on, the other parameters of this YOLO V8 model. Since it took some time for downloading the object detection video. So now I can play the video. So as you can see here, the stop sign is detected with a higher confidence level. This video is taken in the car. Results. So as we can see here, our YOLO V8 model has produced two outputs, which is in video detection with a confidence level of 0.99 followed by image detection with a confidence level of 1. It is considered to be a higher level of confidence in both the object detection models. Followed by the evaluation model of the overall performance. This consists of variation of parameters such as box loss, classification loss, DFL loss, which is distribution focal loss, matrix per precision, matrix per recall, validation box loss, validation classification, validation distribution focal loss, matrix per MAP, which is mean average precision 0.5 and mean average precision 0.5.95. With these evaluation parameters, we can say that our YOLO V8 model has a higher accuracy and also precision in predicting or detecting the stop signboard.
For conclusion, the stop sign detection project using YOLO V8 showcased successful real-time identification of stop signs in static images. However, challenges arose in dynamic video scenarios, revealing the need for optimization, especially in real-time video processing. The findings suggest future research direction, including refining model parameters and exploring dataset augmentation for improved performance in dynamic settings. Overall, the project contributes to enhancing road safety and traffic management through advancement in computer vision for traffic control systems. Thank you, Doctor.